In this video, we're going to look at volumes of revolution again, where the axis is not going to be one of the cardinal axes of the x and y axis. We're going to work with a region bounded by y equals square root of x, and y equals 0, which is this boundary, and x equals 4, so that defines this shaded region. We're now going to rotate around a line off-center though, y equals -3. So that's this axis here. If we're going to rotate around that axis, let's add that as a circle here, we're going to cut perpendicular to that, because if we cut perpendicular, we're going to get circular shapes. In fact, we can imagine a mirror image of this shape down here. This is going to get rotated around all the way down to here and have this kind of cross-section. So we could try to get a third dimension on here. I won't go too far down that road because I'm not sure how helpful it would be. But we can imagine there's a large bore hole through the center of this shape because this is all empty, and we have essentially a bowl on the outside of that. You can imagine taking a loaf of bread, a round loaf of bread, and hollowing out the middle. It would look like that, roughly speaking. We'll clean this part here up a little bit so we can add some more diagram elements. The nice thing about this slicing approach, though, is we have a familiar shape. We're going to have a ring. The volume of a slice is going to equal the area of a ring times the thickness. Area times one other dimension gives us volumes. The thickness, super easy. We're taking a little thin slice this way, that's in the x direction, so we're going to use delta x as our thickness. The area of the ring is going to be an outer circle minus an inner circle area. Find the area of the whole circle from here all the way out to the edge, build a circle out of that, and then subtract the area of the hole in the middle. And there's our delta x thickness. Our challenge now is to find these inner and outer radii, and to do so for every slice. The idea is someone tells us what x is, and then we figure out what the radius is. The nice thing about this is, at least on the inner radius, the inner radius is always bounded by this, and here you have to use your diagram carefully. This distance here, this is the x-axis, this is y equals 0, this is y equals -3. How far apart are those two lines? That's right there in the picture. There are 3 elements apart. Don't get distracted by signs. We're looking for distances. So this inner radius is 3, no matter where we take our cut. What about the outer radius? Let's use black for that. We'll make it a bit more official here. A little more straight. There we are. So that outer radius is a little trickier. It's defined by y equals root x. Depending on where we slice, we're always going to be stopping at that curve. However, we can't just talk about the y value, because the y value is actually just this part here, the distance from the axis up to that y value. For example, if we said y was 2, and that's fine here, the radius is actually 5. Well, how do we get that? We've seen this kind of structure before. Oh, there's always a 3, and then I'm going to add whatever comes after that. So it's actually going to be the y-coordinate on the graph plus 3, or the square root of x plus 3. And again, you can verify this. At this point here, when x is 1, the radius is 3 and 1 more, which is 4. 3 and 1 more is 4. Check it at the endpoints. Do whatever you need to do to convince yourself that the graph itself, the function value y, is not going to be enough here. By moving things off the axis, we're essentially adding 3 to all the radii, inner and outer. And the best aid for that is to have a good clear diagram, because if you look at this diagram here, we can clearly see the 3 distance here, and then the y value on this graph is always relative to the axis down here. So we always have 3 plus that last little bit of distance. With that, we can build our volume calculations. We're going to have a common factor pi. The outer radius is root x plus 3. We're going to square that. And then the inner radius is always 3. That was over here. We're going to square that. And then we have delta x. And that's the hard part done. From this point on, we're going to be turning it into a standard integral question, and that is going to be fairly straightforward compared to what we've done already. The one thing to note on this diagram is we're going to be taking dx as our integral variable, so that means we're going to be slicing from here out to x equals 4, x equals 0 to x equals 4. So our total volume is going to equal the integral from x equals 0 to x equals 4, common factor of pi, and going back a page, square root of x plus 3, all squared, plus 3 squared, and the last element, the delta x, gets converted when we turn it into an integral to a dx. Ready to go? We now have a standard integral. There's nothing easy to do with this squared term. As soon as we have things squared with something complicated inside, like a root, we're not going to be able to do anything too much with it in its current form. So one of the options we can take advantage of is expanding this, taking the square and getting square root of x squared. That'll just be x. We're going to have 6 root x's. And then we'll have 9. And I forgot this negative sign here. It should be negative. And then minus 9 dx. And now we can cancel a few things, tidy up a little bit further. We're going to have pi times the integral from 0 to 4 of x plus 6 root x dx. And that is a totally straightforward integral now. We can take the powers, add 1 to the power, divide by the new power, and so on. We'll have pi x squared over 2 plus 6. This is x to the 1/2. We'll add 1 to the power to get 3/2, divide by the new power, and evaluate that between 4 and 0. The pi applies to all of that. Let's tidy one more stage. We'll have x squared over 2. 2/3 of 6 is 4. X to the 3/2. And then we'll do the subbing in. So that was a tidy. And this is our sub in. We'll have pi times 16 over 2. 4 times 4 to the 3/2. We'll think about that for a few seconds. Minus 0 plus 0. So that's 8. 4 to the 3/2 is actually 8 as well. So we're going to end up with pi times 8 plus 4 times 8. That's 5 times 8, which is 40 pi. Or if you like numeric values better, 125.66 cubic units. Perfect. Again, remembering the process that we had to go through to get to this integral, you should be able to see here it was an r outer, and here this is an inner radius, and there's the squares and the pies to turn it into circle areas. But we could see the outer radiuses, outer radii, always having this 3 plus the y-coordinate element to them, whereas the inner radii were always 3. Every time we draw them, it was 3 because we're measuring from y equals -3 to the boundary of that region.